Alright folks, so I lost the video that I originally made with my class. I'm going to re-record here after school and try to run through some that people asked me in class today. So my apologies if I don't get to answer your question. You can always just ask myself or Mr. Goff if you have any further questions on your review packet, but here we go. So, questions on letter E, some students in class today, specifically about number 2. I believe the first thing I kind of talked about here was the fact that you were asked to do this in point-slope form. Point-slope form is kind of a less comfortable way to write the equation just because you're less familiar with it, right? So mostly we're familiar with slope-intercept form. And in order to write an equation slope-intercept form, you need both a slope and a y-intercept, which in this situation we have neither a slope nor a y-intercept. We're given points, but no slope. So we have at least get slope here, right, to do anything. So slope right, y2 minus y1 over x2 minus x1, so applies to negative 5/6. At this point, we can go ahead and put that m into point slope form, and then pick any one of these two here to solve a substitute for y1 and x1. You can see how I have both options right there. There is, of course, no need really here to use slope-intercept form. Point-slope form is fine. There's no need to solve here. I know if we were to graph these on our graphing calculator, yes, you'd need to get the y by itself there, subtract the over, adding the 2 over, what have you. But given the fact that we're just trying to write the equation along, we're done here, so we don't need to continue. Okay. I think then moving to letter F, we have some questions here as well, so I'll try and focus in on things. Again, these are a little bit funky just because we're asking you to both identify and then correct the mistakes that happened here. The first question I got was on number 2. I was asked basically, where is the mistake, what's going on? And so the question I ask is, what is being raised to the negative 2 power right here? Okay. The answer is only the x is being raised to the negative 2 power, so only the x should then, quote unquote, move to the denominator. The 3 should stay where it is. Okay. So this 3x to the negative 2 is equivalent to 3 times 1 over x squared alone, so it's 3 over x squared. This right here, okay, some people might think is equal to like 3x to the negative 2, right? But it's not the same thing, right? Okay, 3x to the negative 2 would actually be 1 over 9x squared here. So you can see that the difference is here. If it was the quantity 3x to the negative 2 would look like this, with the way it is, it looks like this. So these two things really don't have any connection whatsoever. It's just not right. Okay. Number 3, just have a simple here, I guess, about how to simplify this exactly, since no way to simplify it. And the answer is that's kind of all these things are not equal, so we can put a little not equals sign, but ultimately there's no way to simplify this any further. Okay, so we just leave that as the square root of x plus 9. That's not obviously equal to x plus 3 there. And I did kind of talk about how the square root of x squared in an equation setting, you do want to in this, like if you simplify something like this, you do want to have x as both positive and negative 3. Okay. Number 4, I was asked about this one too. Again, just to kind of go over, why it is the way it is or what's wrong with it. In this case, I like to use kind of an example here. So, again, sometimes we run across problems as students that we're not really sure what is right and what's not right. Okay, and this is sometimes you can kind of convince yourself by making the more complicated problem a simpler problem. So, for example, let's say that you have this, and you're like, I wonder if I can break this up over addition, break up the denominator over the addition there. Well, one way we can kind of do that, or one way we can kind of help ourselves to, make the problem more simple, is to change all these powers of x to just be numbers. So we'll just make it 6 plus 2 plus 3. Okay, and we want to know, is that the same thing as then breaking up the denominator, saying 6 over 2 plus 6 over 3, right? We want to know, can we break up that denominator like that? Okay, well, let's continue simplifying here. 6 over 2 is easy, that's 3. 6 over 3 is 2, and so that's going to give us 5. If we simplify this as we should, it'll be 2 plus 3, which is 6 over 5, is equal to 6 fifths. 6 fifths is not the same thing as 5, and so in general, we can't break up. That's a counterexample there, right, of that desire to break up the denominator. So in general, we're not able to break up the denominator over addition like that. In fact, it doesn't really ever work. Okay. So what can we do here? Well, the best we can kind of do is what you kind of see right here. We can factor x at the denominator, cancel out with the x to the 4th up here to make it x to the 3rd, and we're left with 6x cubed over 2x, and that's about as good as we can get. We just have to be careful here. Addition in the numerator can be broken up over the denominator, right? But addition in the denominator or subtraction in the denominator can't be broken. It must stay where it is. Now, that's not the same thing as when we have multiplication. So, for example, 6x to the fourth over x times x squared plus 3. This denominator can be broken up over multiplication, right? Because the properties of multiplying fractions is that you just across top multiply across the bottom. So there is an example of when you can break it up. But adding fractions together, you don't add the denominators, you only add the numerators, which allows us to break up those numerators over addition and subtraction. Moving on. All right, here for G and G numbers 1 and 2, the x's were there, and then it was root 2 here. Here was x. It was supposed to be x times the square root of 3 here, and then x. I kind of got rid of the x's when we were talking about the trigonometry stuff down here. But really, when it comes to these reference triangles, okay, and then your little diagram here that describes, the different trig functions are positive and in what quadrants. And all, these three things will allow you to evaluate any kind of trigonometry that you might run across without a calculator. Okay, so zooming out here some, didn't have too many questions on the trigonometric values here so much, just kind of the rectangles and things. Did have a few questions on evaluating arcsine, tangent inverse, arcsine, and arcsine here as well. So some things to remember. First of all, arcsine is the same thing as saying sine inverse of root 3 over 2. Here, tangent inverse, right, is the same thing as saying arctangent, arccosine is the same thing as cosine inverse, arcsine is the same thing as sine inverse, right? They're synonymous terms, it's just two different ways to write the same thing. Arcsine of root 3 over 2, right, so how do we evaluate that? Well, the question is, we're trying to answer here, so arcsine or sine inverse, those are kind of inversed, they're inverses, really, of the original trig function. Trig functions, right, you always take the trig function of an angle, and then the output is a ratio. Again, angle in radians or degrees, you plug it in, it is the input into a trig function, and the output that is ratio. Due to inverses, right, where the x's and y's flip-flop, when we talk about inverse trig functions, now the input is a radian, the output is an angle in radians or degrees. So, as you can see here in a normal trig function, we're taking cotangent of an angle. Here in an inverse trig function, we're taking the arcsine of a ratio, and our output will be an angle. Okay, but still the question remains, how do we evaluate arcsine of root 3 over 2? Well, in a similar fashion, how we evaluate something like sine of pi over 4. Go up to your reference triangles here. Instead of asking the question, instead of saying, sine of, 3 pi over 4 gives what, we're now trying to figure out what angle, when you take the sine of, gives you root 3 over 2. So which of these angles here will result in us getting root 3 over 2? Well, since it's sine, we need to have root 3 be the opposite and 2 be the hypotenuse, right? Opposite of hypotenuse, root over 2. So if this is opposite hypotenuse, then that's opposite pi over 3. So our angle here, pi over 3, and sure enough, there it is, pi over 3, our answer. Okay. I'm going to negative 1 for right. Move on to arcsine. Arccosine of 1. Okay, so now we're in a little bit of trouble here because we can't get a ratio of 1 using cosine for any of these right triangles. But we have to remember that cosine is equal to 1 at a 0. So there's our angle. All right, and that's the trig right there. Sorry, I was recording myself because I had deleted the original video that I made. So that's
alright.
So yeah.
Do you have any more textbooks for AD?
I do.